All right, welcome everyone. For those of you watching on YouTube, this is our 7th live stream geometry session. So far we have 4 other people here now. Rodrigo from Brazil, Matej from Croatia, Agastya from India, and Craig from the US. So I'm sure a few more people will pop in as we go. But for now, let's get started on the problems. I'm going to share my screen, just a second. Let me try to find it. Hold on just one second. I think it's this one. Yes. All right. So can you guys see the first problem? Oops. Are you guys able to see it?
Yeah.
Yes.
Yes.
All right. So we have an acute triangle ABC. So this problem is from Poland in 2019. So it's from their math competition. X and Y are an AB and AC, so that AX is equal to AY. And XY passes through the orthocenter. So let me see. I'm going to draw the orthocenter. I think it's 4. It should be the orthocenter. Okay, and then, so how would we do this? So I think what we want to do is I'll draw the angle bisector, and then I'll draw the perpendicular from the orthocenter. Okay, so then these should be points X and Y, right? So that's X, that's Y. And then we draw, so I'm gonna hide a couple things so it just looks a little cleaner. All right. And then we draw the circumcircle of AXY. And then we draw the line's tangent at X and Y. Okay. Let's see if I can find the tangents. All right, let me move the diagram around a little bit. So those intersect at point P, and we want to show that A, B, C, and P are cyclic. All right. Sorry, hold on one sec. I'm going to stop sharing my screen for just a second so I can check Discord, because I hear a few people on it. All right. I'm just going to mute my Discord for now. All right. So, sorry about that. So I'm going to go back to sharing my screen. All right. So here's the problem. Oops. Okay. All right. Let's see where we can start. First, let's see, is that actually true? A, B, C, and P are cyclic? Okay, so that's true. How do we prove it?
I don't know if it's true as well, but it looks like P is the midpoint of the arc ABC.
Yeah, that would mean that A, E, and P would be collinear. Yeah, that does look true. Let's see. Yeah, that has to be true by symmetry, actually. actually.
Yeah.
Because basically P by symmetry, it lies on the bisector of angle XAY. So yeah, I mean, basically we know A, E, and P are collinear, right? So yeah, where could we go from there? Let's see. This looks a lot like, do you guys know the property where if you take like the midpoint of BC and you take like the two tangents to, so I'm going to draw the perpendiculars from H to A, B, and BC. So basically, since H is the orthocenter, that means BF is perpendicular to AC and CG is perpendicular to AB. Okay. So, and D has to lie on the circumcircle of AGHDF, right? Because angle HDA is 90 degrees. I'm going to draw on the midpoint of BC. Let's see if that helps. So yeah, you know IF and IG are tangent to the smaller circle. I don't know if that helps at all, but that's a property. Let me try to make the diagram nicer. But yeah, it's a property. So I've discussed this on my channel before, but IF and IG are tangent to that circle. I don't know if that helps us prove that PY and PX are tangent to this circle, but maybe it does. Let's see. Yeah, I guess there's a couple ways we could do this, right? We could try power of a point, which we could show AE times EP is BE times EC. I don't think that would probably be super helpful. Or we could show angle PBC is equal to angle PAC. Maybe that would be more helpful. I'm trying to see if we can do like an angle chase to do that. So we could also use that the reflection of H over BC lies on the circumcircle of ABC, right? Because we have to use that it's the orthocenter somewhere, right? Just label this point right there. So this is kind of, so I'm just going to draw in the circle for now, even though we're trying to prove it exists. So yeah, we don't know P lies on the circle yet, but like if we, let me try this. If we let K be the midpoint of arc BAC, then basically we want to show that AXJY is similar to KBPC. But we know triangle AXY is similar to triangle KBC. Yeah, what if we think about it the other way? What if we let P be the midpoint of arc BC, and then we want to show PX and PY are tangent to this circle? I think that might be an easier way to think about it. So like, what if I hide PX and PY, and I define P to be the midpoint of this arc, and then I want to show PX and PY are tangent to the circle? I kind of like that better. So what would that mean if PX and PY are tangent? That would mean angle PXY is equal to angle A, right? I could check that. Let's see. 67.9 degrees, 67.9 degrees. Okay. So that's kind of interesting. What does that say about, so if angle PXY is equal to angle A, and angle AXD is 90 minus A over 2, and that means those would add up to 90 plus A over 2. So basically, we want to show angle BXP. I think we want to show angle BXP is equal to A over, no, we want to show angle BXP is equal to angle AXD. Yeah. Okay, that's interesting. Can we show angle BXP is equal to angle AXD? I think maybe we can. So is J the in-center of triangle PXY? I think that might be true. Yeah, J is the in-center of triangle PXY. How do we show that? We know it lies on one of the angle bisectors, so we know it lies on the angle bisector from P. But let's say we didn't already know that PX and PY were tangent. How would we show that?
So we have to prove that JXA is 90.
Yeah, we know angle JXA is 90. Yeah, maybe that just solves it, because yeah, okay, I think we've solved it by the in-center x-center lemma. I think you're right. Angle JXA is 90 degrees. Okay. So I'm gonna write up the solution, and then we can do the next problem. All right, so I'm gonna call this P prime for now, and I'm just gonna say let P prime be the midpoint of arc ABC of the circumcircle. Hold on just a sec. It won't hide. I'm trying to hide segments PX and PY. Let's see. I might have to delete them. There we go. Okay. So where did I use that H was the orthocenter though? Trying to think. So I had to use that somewhere, right? I thought I had this, but I'm a little confused. So I wanted to show angle BXP prime is equal to angle AXY, right? So yeah, we know angle AXJ is 90 degrees. No, I think it's not enough to show that angle AXJ is 90 degrees to show, we still have to show more to show that J would be the, yeah, no, that all by itself doesn't prove it. We still need one more step. Let me try something here. So we know J lies on the bisector of XP prime Y, right? So if we can show A is the X center of triangle P prime XY, that would solve it. Oh, but that's just equivalent to what we're trying to prove, I think. Yeah, but basically we want to show A is the X center of triangle P prime XY. So I wonder if that's true by an angle chase, because just thinking here. So basically we want to show the distance from A to XY is the same as the distance from A to P prime X. I'm seeing so many different equivalent things here. I'm trying to figure out which one is the best to work with. Okay, I think I have it. Let me just double check. Okay, so here's going to be my strategy. I'm still trying to figure out where I use that H as the orthocenter. So I wonder if, so it looks like these three circles meet at a point. And I think IG passes through P prime. Actually, I'm not 100% sure. Let's see. Not necessarily. But basically, I mean, we know by symmetry that AP prime is an angle bisector of XP prime Y. So that means if we label these two intersection points, K and L, A has to be the midpoint of arc KL. And then at the same time, P prime is the midpoint of arc BC. So we can do an angle chase to show that angle BXP prime is equal to angle CYP prime. Oh, but actually that's kind of obvious. That doesn't do much. Yeah, there's still one more step we have to do. I feel like triangle AHX might be similar to triangle BXP prime. That looks like it might be true, right? So AXH is 106.7, and yeah, I think that might be the trick. How do we show that those two triangles are similar? So basically, we want to show BP prime over BX is equal to AH over HX. That would be one way to do it. So we can calculate angle AHX, and we can show it's the same as angle ABP prime. I think we're close. Let's see. Could we try power of a point and then determine ratios of similar triangles? What would you like to use power of a point on? So I think triangle BEP prime is similar to triangle ABP prime by an angle chase. Yeah, so P prime B squared is equal to P prime E times P prime A. I feel like we're so close here. There's just like one step missing. Let's see. Let me try something. Yeah, okay. I've got that it's equivalent. We want to show that CH and PX concur on the circle. If I can show that, I think I've solved the problem. I wonder if that's obvious somehow. Is it obvious that CH and P prime X concur on the circle?
Can you just mark the intersection of CH and E?
CH and the circle?
No, the intersection point of CH and AE.
Oh, and AE, sure. Oops, sorry.
So GX and GXID must be coencyclic, right?
Yeah, GXID has to be cyclic.
So if we know that angle BXP and angle AIG are equal, then they will conquer at the circle.
Ah, I see what you're saying. We want to show BXP prime is equal to AIG. Yeah, I think we need to use similar triangles somehow. So we have P prime. I think I have an idea. We have P prime B squared is equal to PE times P prime A, and we want to show. We have P prime X. We want to show P prime X squared is P prime J times P prime A.
So is that XJ is parallel to BP prime?
Is XJ parallel to BP prime? Let's see. I don't think so.
No.
This problem looks so familiar. Like, I feel like,
Can you please check again that GJ is parallel to BP prime?
Oh, GJ. I think that might be true. That looks like it could be true. Let me move around the diagram. Oh, no, not necessarily. Okay. Yeah, it feels like there has to be a way to show AXH is similar to P prime XB. And somehow we have to use it.
I think the fact that angle ADX is 90 plays an important role in the answer.
Yeah, that angle ADH is 90 or ADX is 90 degrees. Yeah, what if we drop a perpendicular from P to AB, right? From P prime to AB. So we know AP prime K is similar to AXD, and we want to show that B cuts it in the same ratio. So yeah, I'm thinking of all kinds of things. So basically, I mean, so BP prime is equal to CP prime, right? And angle XBP prime is 180 minus angle YCP prime. So we can rotate, basically, if we rotate triangle YCP prime, so I'm going to do this. Oh, whoops! I should be like this. Sorry. Yeah, I think this might do it. Let's see if this works. So basically, sorry, the diagram's a little messy. But basically, we can take triangle YCP prime and we can rotate it so that CP prime overlaps with BP prime, and then Y will go to this point K. And we can do that because we know angle YCP prime plus angle XBP prime is 180 degrees, right? What I wonder if that helps. And then triangle P prime XK is isosceles, right? So P prime XK would be isosceles. And what did we want to show? We want to show that both of those angles are equal to AXY or AYX. So we want to show triangle P prime XK is similar to triangle AXY. Or that's the same as showing triangle AXP prime is similar to triangle YXK. Hey, Timo, thanks for joining. Did you finish taking the German TST? Yeah. So yeah, we've spent almost 40 minutes on this problem. I feel like it might be easier than we're making it, but yeah, it's an interesting one. So what was I thinking? We want to show AXY is similar to P prime XK, which is the same as showing triangle AXP prime is similar to YXK. Ah, it's in a while. Okay, the German TST. What if I drew segment YK? It looks like YK passes through J, and I think that would likely solve the problem if we could show that. Yes, because that would show that those two triangles are similar.
So triangle XKY is similar to triangle XP prime A.
If we can show that, that would solve the problem. And is that the same as showing HB is parallel to YK? Yeah, Another way of saying it is we want to show HB is parallel to YK. So I think I have an idea. Let me check a few things. Are these triangles similar? 33.9. Yes. Okay. So can we show XH over XB is HY over YC? I think I have it. So triangles XBH and HYC are similar by an angle chase. And I think that gets us close to solving the problem. Okay, yeah. So I'm going to start writing this up. Let me hide a couple things, but yeah, I have the solution, and I see where we use that H as the orthocenter. Okay, so let me hide a few things that I don't need. Let me just, okay. Do I even need that circle? Okay, I'm going to hide P prime X and P prime Y, or delete them maybe for now. Okay, so here's how I'm going to write the solution. Okay, so P is the midpoint, P prime is the midpoint of arc BC, and we want to show that P prime is equal to P. Okay. Now I'm going to say, so by symmetry, P prime X is equal to P prime Y. So since triangle AXY is isosceles, and P prime lies on the angle bisector of A, by symmetry, P prime X is equal to P prime Y. All right. So that means that we can rotate. So I'm going to add in one more step. So we also have P prime C is equal to P prime B, and P prime CY equal to 180 minus P prime B X. So that means we can rotate the triangle. Whoops, sorry. So then we can rotate triangle P prime CY so that P prime C goes to P prime B, then let y go to k. All right. So A, B, and K would then be collinear. All right. And then once we know that, now I'm going to show triangle BXH is similar to triangle CYH. So that's true by an angle chase. So we have angle BXH equals 180 minus angle AXY, which is 180 minus angle AYX, which is angle CYH. So that shows that one of the pairs of angles are equal. And then the other is also easy to see as the same. So we have angle ABH is 90 minus angle A, which is or all right angle XBH, which is angle YCH. Okay. So this step is where we use that H as the orthocenter. And so therefore triangle BXH is similar to triangle CYH. Okay. And so that means that BX over XH is equal to CY over YH is equal to BK over YH. So all right. Which means that YK is parallel to BH. All right. I'm trying to remember what I was doing here. I feel like I had this in my head. Now I'm trying to. Hey, Aryaman, thanks for joining.
My pleasure, sir.
All right. Where was I? So once I knew that those two were parallel, I wanted to show AXP prime was similar to KX. Yeah, what was I trying to do? I wanted to show that AXP prime was similar to KXY, I think, right? And then, yes. I know I had this. Where was I going with this? So we have YK is parallel to BH. I wanted to show Px and P prime X and P prime Y were both tangent. Trying to remember where I was going with this. I feel like I had it in my head, but I lost where I was. I lost my train of thought. So let's see. We want to show AXP prime is similar to KXY. So BX over XH is the same as KX over XY, since those two are parallel. And we want to show that's PX over XA. Okay, I think I have it. Hold on just 1 second. I think I have it. So So we have kx over ky is bx over xh. So kx is kb plus bx, which is the same as cy plus bx. Okay, so yeah, I feel like there's just a lot going on here, but I feel like basically we know we're trying to show that P prime XK is similar to AXY, but we know B splits the segment XK in the same ratio that H splits the segment XY, right? So basically B would correspond to point H in those two similar triangles, right? And also we know angle BP prime K. We know the whole triangle BP prime K is congruent to CP prime Y. Okay, so if these two are parallel, then we can calculate angle XYK. And I think we can, all right, let me write this out. So first I'm going to label this point of intersection here. I'm going to call it E. And then let's see. So XYK is that should be XHB. One sec, I see the chat. Just gonna wait till it's finished. It's 180 minus ABH minus HXB. And then by an angle chase, that's equal to half of angle A. I might write out this angle chase in more detail, but basically that means that Y, E, and K have to be collinear because we have angle XYE is equal to angle XAE, which is half of angle A. So Y, E, and K are collinear. All right. And then I'm going to read the chat. Ariaman, maybe after the session, I'll take a look at that, but I don't think I could solve that right now. Okay, so where was I trying to go with this? So Y, E, and K are collinear. And so I wanted to show AP prime X was similar to KXY, I believe. Let's see. And then I think an angle chase might do it. So hold on just a sec. So that means, so we're trying to show KXY is similar to A prime XP. We know one of the angles are similar. We show another angle is equal. I feel like we're so close here, but it feels like it just has to solve any second, but I can't see it. Guys have any ideas?
Michael, I was thinking independently on this problem, and I think I solved it in a different way.
Oh yeah?
And yeah, it's very simple. Do you know the Pascal configuration?
Pascal's theorem, yeah.
Yes. So basically, can you take the line BH and intersect the circle of ABC at a point? I don't know, at some point.
Yes.
Yeah. The thing is that these points collinear with B prime and Y.
You're saying I, Y, and P prime are collinear.
Yes.
Ah.
Yeah, and it's tangent to that circle as well.
How do you know that it's tangent?
In fact, you know that IY is tangent because the angle that IY makes with the line XY is A.
The angle that IY makes with XY is A. And I'm trying to see, okay, so basically use Pascal's theorem. So okay.
You wanna
Yeah.
show that the intersection of JX and IY lies on the circle, right?
Yeah.
And this is Pascal theorem.
Okay. And then it's the, so you know it lies on the circle. We don't even need it's the midpoint. I'm trying to see where do we use that H as the orthocenter? Is it just some angle chase?
You use that as your center for taking the I and J, I think.
But what if like couldn't we have done that with any other point? Like if we let P be any, if we let like, I don't know, Q be any other point, like is all we need the fact that H, X, and Y are collinear? Like do we even need that H is the orthocenter?
I think you need that is isosceles. The AXY is isosceles.
You need that as isosceles. Let me just try for the heck of it. Like, what if I did something like this, and then, whoops, sorry. Yeah, I'm just trying to think where we use all the conditions. Like if I did something like this, and then that, and then I let it meet at 2 points, right? then OM and PL, would those meet on the circle? Yeah.
Yeah, that's Pascal.
So do we even need yeah, I'm trying to see where we even use that H is the orthocenter. Oh, because we need to know that they're tangents. Okay, so
Yes.
and okay, so let me see. So we have that configuration, but we can show that they're collinear because the angle that IP makes with XY is equal to angle A, and we can calculate that. Let's see, how do we I guess that's probably just an angle chase, right? I'm trying to think. So I'm gonna erase this stuff and try to do it your way, because I think your way is probably the simplest way. Although I'm still interested in trying to finish the problem. Like after the session, I think I'll try to see if I can do it my way. But I think your way is really much simpler. So let's see. Okay, so sorry, I'm gonna hide a couple things. Okay, so by Pascal's theorem, Jx and Iy are concurrent at a point P prime. So I'm gonna write that. Okay. On the circle. So that's really probably like the converse of Pascal's theorem. We don't yet know it's the midpoint, but it's probably not that hard to prove, I would guess. All right.
From that point, what is missing is proof that Jx and Iy are tangents, right?
Yeah, exactly.
Yeah, this is just angle chase.
Okay, so the angle that XY makes with IP prime, you're saying that's equal to angle A. How do we show that? Oh, because, okay, if we could show that P prime is the midpoint of arc BC, then I think it would just be an angle chase. Is it obvious that P prime is the midpoint of arc BC?
We know I is the reflection of H over AC. And so angle YHF is equal to angle FAY. And in the same way, angle GHX is equal to XJG. And those angles have to be the same.
Okay, so I is the reflection of H over AC. That's a well-known fact about the orthocenter. So therefore, angle what did I just say? Angle IAC is equal to angle HAC, but I think, hold on just a sec. I had it in my mind, but I just forgot it.
We know HY is equal to YI.
HY is equal to YI.
And so, because HI is perpendicular to AC, and therefore YHI is equal to HIY.
Ah, okay. So YHI is equal to HIY. All right. And then similarly, GHX is equal to CJ P prime. And then if we combine the two, it's fairly easy to see that GHX is equal to angle FH or angle YHI. So I'll just write this out. And then these are also equal to angle A. And so therefore P prime is the midpoint of arc BC. All right. And then once we know that, now we can do an angle chase because we can show basically we can calculate angle XYP prime and show it's equal to angle A. So I guess another way is we can trying to think how to phrase this. So I know I can calculate angle CYP prime. And then I could probably use that. So yeah, I'm just going to write this out. So angle CYP prime, it's half the sum of the two intercepted arcs. Okay.
We know CYP prime is equal to AYX, and that should finish it. Because of the symmetry.
So are you using this fact right here that it's half the sum of the arcs, or is there some other?
This fact isn't needed. We know angle AYX is equal to angle AYI.
Ah, okay.
And yes, and this should finish it. Because then angle XY P prime is equal to XAY.
Okay. So in fact, I think a lot of this I didn't really need, right? So I'm gonna simplify this quite a bit. It's actually much simpler than I realized. So So we have that. And so then we can do an angle chase. So that means angle XYP is equal to 180 minus 2 angle AYX. I'll just put HYX for just to match what I did before, which is 180 minus 2 times 90 minus, or HYX is half of 180 minus angle A. And that is equal to angle A. See how this turns out. And then similar, so that means that P prime, I'll call this P prime. So P prime Y is tangent to the circle. And then similarly, P prime X is tangent to it. We'll just write, and similarly, and so that means that P prime equals P. Which means that A, B, C, and P are cyclic. Thanks for bearing with me on this one. All right, let's move on to the next problem. Yeah, that was a good call finding Pascal's theorem. All right. Here's another one from Poland. So we have a triangle ABC where AB is less than AC. E and F are the feet of the altitudes from B and C. All right. Gonna delete. When we draw the tangent to the circumcircle at point A. Let's see. Here's my circle. I gotta click more. Here we go. So we draw the tangent to the circumcircle at A, and it intersects BC at a point P. I think it actually, and I think P might actually be concurrent with EF. I have a feeling that's true by properties. Oh no, P is not necessarily concurrent with EF. But I find in a lot of these problems there's stuff you can do like with inversion. Let's see. So this is point P. And then the line parallel to BC going through A intersects EF at Q. Okay, so that would be point Q. Oh, I feel like I've seen this before. Yeah, I feel like they took this from another competition, but I think I already know the solution actually. So I think it uses point circles. So let me think. I think I've already seen it, so I will let you guys try to solve it. But my hint is that it uses point circles. Okay, so we want to show PQ is perpendicular to the median from A. Oops. Let me just see if I can remember my solution with point circles. So obviously D is the center of the circle through BC. B, C, E, and F.
Is the reflection of A over PQ the HM point?
The reflection of A over PQ.
Yes, I think it should be.
Okay. Is that the, did you say the endpoint?
The HM point, the Humpty point.
The Humpty point. I think it probably is. Yeah, yes, because it lies on that circle, so it has to be. So yeah, I see a solution using point circles as I mentioned, but so yeah, you guys can either try to find that one or you could try to solve it a different way. But yeah, if you guys want me to share my solution, yeah, just let me know. I'll be right back, just a second. So I think I've seen Osman Now do this exact problem. So have any of you guys seen Osman Now's YouTube channel? I know Ram has seen it, right?
Can you name the channel again?
Osman Now.
Oh, yes. Osman Nal.
Yeah, I think he's done this exact problem on his YouTube channel. But yeah, I think Poland just took it from another competition. So yeah, I'll let you guys work on this for maybe like 20 or 15 more minutes, and then I'll just share the solution that I already know to this problem. So let's see, I'm going to try to solve it using Timo's idea. So you said that A prime we want to show is the Humpty point.
If we know that this is the Humpty point, we are done, I think. Because point P has the property that P is the center of the Apollonius circle.
Yeah, if we know A prime is the Humpty point, I think it's pretty clearly finished, because basically that means that GA prime is perpendicular to AD, and by definition we also know that AA prime is perpendicular to PQ, right? So I mean, yeah, we know that A prime and B are collinear. So, yeah, no, I think that would solve the problem immediately if we knew that. See you, Craig. Yeah, thanks for joining us. Have a good rest of your day. All right. 1 second. All right, see you, Agastya.
Bye.
Thanks for joining. Is it true that if you take the Humpty point and you reflect it over BC, it lies on the circumcircle? Yes, that's just a property of the Humpty point in general. So we have to show that A prime is the Humpty point. Or you could work at it the other way. You could take the circumcircle of AF. I'll just call this H. You could draw the circumcircle of AFHE, and you can let it meet AD at a point A prime, and then you want to show A prime is the reflection. So I guess you could work at it either way. See. So, yeah, I'm wondering, so if it were true that A prime were the Humpty point, then its reflection would lie on the circumcircle, right? So basically that would mean like GI is parallel to a double prime. But I'm going to give this a different name. I don't like double primes. I'll call it K. Basically, that would mean GI is parallel to a K. So is PH and A prime? No, those aren't.
Can you draw in the circumcenter of ABC?
Yes. Let's see. What have I named that circle? Sorry, I'm just trying to. What's the circle through A, B, and C? C. Okay. All right. I'll just call it O.
And can you draw in PO?
Yes. And it looks like it meets on AI. Oh, not necessarily. Yeah, I'm sorry to kill the, I hope this doesn't kill your enjoyment, but yeah, the solution using point circles is super slick. Let's see if we can figure it out this way. So basically, like, we know that APBO is cyclic, right? And if A is the Humpty point, then K also lies on that circle. Is that obvious? Hmm. see. Guys, have any other thoughts? All right, I'll give it a couple more minutes and then I'll just show you guys the solution I have that I've seen.
Okay.
I think there's also, yeah, I've also seen another solution using projective geometry that's a little bit longer. But yeah, I'm sure there's a way to do it with Humpty points, like the way that Timo's mentioning. So we know it's a well-known fact that AO is perpendicular to EF, right? So maybe we could show the angle that AO makes with AD is the same as the angle that EF makes with PQ. Not sure. Yeah, so we'd want to show angle OPD is equal to angle PQF. All right, just for the sake of, I guess, keeping it interesting, I'm going to show you guys the solution using point circles, which is really, really slick. So let me delete a couple things in the figure. Let's see. So, sorry. Okay, we want to keep that. We want to keep that. Okay, so it's really just like the solution's really just a few lines. So I don't even think we need O for the solution. So first of all, it's clear that BFEC is cyclic. So I don't even think, yeah, it's cyclic with center D, right? Okay. So now consider that circle BFEC and the point circle A. So it's like a circle with radius 0 centered at A. So I'm going to show that P lies on the radical axis of those two circles using power of point. So we have PA squared is equal to PB times PC. So that's true by power of a point. But PA squared, that's the power, that's also the power of P with respect to the point circle A. And PB times PC is the power of P with respect to the circle BFEC. So P has the same power with respect to the point circle A of radius 0 and BFEC. You guys see that? Isn't that cool?
Yeah.
And then Q, we can show something similar. So AFHE is cyclic, so that's pretty obvious. And it's well known that AQ is tangent to that circle, so I'm going to draw it in. So since AH is a diameter and it's perpendicular to BC, it's clear that QA is tangent to that circle. And so we can use power of a point again. So we have QA squared is equal to QE times QF. And so Q has the same power with respect to the point circle A and the circle BFEC. Actually, I might as well just copy this statement, but replace P with Q, right? And so PQ has to go away. All right. So PQ is the radical axis of those two circles. So it's perpendicular to the line joining their centers. So basically that means that PQ is perpendicular to AD. Isn't that a cool proof?